we have calculated, in a very crude and quick way, how to obtain the phonon frequencies of some arbitrary solid. And I actually considered only one-dimensional examples, but the main difference from a one-dimensional chain of atoms and an actual three-dimensional crystal is just the dimensions of this force constant matrix C, which in one dimensions with two atoms is a 2 by 2 matrix, but in three dimensions, if you have n atoms in your unit cell, it will be a 3n by 3n matrix. Then we said that there is this other matrix called the dynamical matrix. The difference between the dynamical matrix and the force constant matrix is just these factors of masses, the atomic masses. And this is why these are sometimes the phrases are used interchangeably in certain even textbooks, not just research papers.
Sorry to interrupt. What are these masses? What did you actually put there in the code or when you do phonons?
Oh, it's the atomic mass. So
the atomic mass, I see.
Yeah, and okay. If the units can be somewhat of a headache every now and then because they are in, grams per, reported in grams per mole, whereas you have the force constants usually in something like electron volts per angstrom square. So keeping track of the masses is sometimes tricky, but yeah, it's just the mass of the atom.
Okay, yeah, thank you.
And the conceptual difference between these two matrices, apart from these factors, though, is, when we say dynamical matrix, we are talking about some dynamics. So there should be both forces as well as the masses in there. This is why D is called the dynamical matrix. C is a force constants matrix. It's just a second derivative of energy. C doesn't know anything about the masses of the atom. So C cannot give you the frequencies themselves. It only tells us how large the forces on the atoms are. But anyway, in the end, you obtain some dispersion like this in 3 dimensions with a big unit cell. You end up with something like a spaghetti plot where you would have like tens of lines in the phonon dispersion plot. Okay, but I said that even though many codes do this automatically, also there are some post-processing / pre-processing tools like PhonoPy, which does this automatically with varying degrees of accuracy. It is good to actually know what the phonons look like, what their forms imposed by symmetry is. So let's talk about barium stenate again. I like this material because it's cubic. It has this relatively simple crystal structure with 5 atoms per unit cell. And if you are going to do these tests in DFT, this is a wide bandgap insulator, so like the calculations are cheaper, easier to converge, and so on. Now, if I want to calculate just the zero wave vector, also known as gamma phonons of barium stenate, these would be the phonons which have the same periodicity as the crystal structure itself. So I can calculate these using this just one unit cell without building a supercell. I will end up with a 15 by 15 dynamical matrix because I have 5 atoms and each atom can be displaced along XYZ separately, which gives me 15 degrees of freedom. Now, even without thinking about symmetry in a deep way, you can already guess that, well, this is a cubic system. Therefore, this 15 by 15 dynamical matrix probably has a block diagonal form into 5 by 5 blocks, and each 5 by 5 block will be the displacement along, say, X direction, Y direction, Z direction separately. So you can really work with a 5 by 5 dynamical matrix and get the phonon frequencies of this material. However, we can go even further than that. Now, what you can do the brute force way is to displace each atom one by one along, let's say, the x-axis. And when you displace, for example, I should say the autoplane, the z-axis, that's what I have in the figures. And say when you displace the barium atom along the z-axis, you look at the force on every other atom, barium, tin, oxygen 1, oxygen 2, oxygen 3, and you write it down in the first column. And then you repeat this for tin, oxygen, and other 2 oxygens. And in the end, you end up with this 5 by 5 force constant matrix. This is literally something I copied and pasted element by element from the output of 5 different DFT calculations. So for each column, you have to do a separate DFT calculation. Now, due to the fact that action equals reaction, this should actually be a perfectly symmetric matrix. But as you see, there are some little round-off errors here and there, like this 3.26, whereas I have 3.25 here, but let's ignore that for now. By dividing these numbers with the masses of the atoms, you can end up with this dynamical matrix. This has this weird units, as I said, that's per atomic mass unit here. And this still carries the same symmetry as the original force constant matrix. That is, it should be symmetric, which it doesn't satisfy perfectly, but it's somewhat symmetric. Okay, and the eigenvalues of sorry, was there a question?
Yes, I wanted to ask you something, Turan. How big or small are these displacements? Because what I see there, you have very small forces for some atom, like 0.2 units eV per Armstrong. Now, at least in some codes, I know that the sort of error bar of the method is Rydberg per Armstrong, not even EV.
Yeah.
In that case, if I do small displacement and get forces of this type, is within the error bar of the method. So can I make larger displacements?
Depends. I would say so. This material is electronically almost like a vegetable, right? It's a wide bandgap insulator. There isn't very strong spin-orbit coupling and so on. So here I would be confident that my error bar is pretty small, like perhaps 0.1 EV per angstrom, perhaps even smaller. But and this should be angstrom square, right? Because electron volt per angstrom would be force, not force constant. Okay,
sorry, yeah, I understand, but what I'm asking is,
yeah,
generally is the concept, how large can I make these displacements of the atoms?
So in this compound, I don't recall exactly what I used. I think I used something like, I must have used something like 0.1 angstroms. Sorry, 0.0.
Okay, that's quite 0.01.
Yeah. Now, if you are in doubt, and especially in metals, this can be an issue. And also when you have materials that are close to a phase transition, or like when you are in doubt in general, it's always good to consider few different displacement amplitudes and make sure that the force increases linearly. So in principle, choosing a larger displacement is better because you would have less error in the forces. But then again, if you do that and if you are beyond the linear regime, then
I see. So that's the problem. I see. So you have to do a few of them to make sure that you are in the linear regime.
Yes.
And then pick the largest displacement, which still keeps you in the linear regime. Because I have an issue exactly as you said for metals, actually, right?
Yeah.
Doing the same calculation for small displacement, I get different phonon, which doesn't make sense. But it's probably because I'm in the error bar of the method, displacement is small, and then I get I see.
Yeah.
And then when you divide by the Dij, maybe that we can take another. How do you actually, if I want to do this by hand, so take the force constants for this material, reproduce Dij. So how do I?
So for example, the first column and first row corresponds to barium, right? So the first, for the 1 element, I need to divide by the square root of mass of barium times the mass of barium. But when it comes to, for example, this sorry, you are not seeing this. Yeah, okay, here. When it comes to, say, this element, this is the
oxygen
barium. Yeah, well, it is the first row, so it's barium, but the oxygen 3 displacement. So it's the
I see. Okay.
Force constant between oxygen 3 and barium. So this one I need to divide by the square root of the mass of barium multiplied by the mass of oxygen.
3, I see.
Yeah. So
okay, I see. Thank you. That's very nice. And Christopher asked when you can get the, probably he should send you an email. Christopher asked on the chat about the presentations. So you can send an email to run the email address to get the slides.
Yeah. So once again, anyone, if you want any of these slides, just let me know. I will be happy to send them your way. There isn't anything unpublished here or any there are some original research results later on in the presentation, but they are all from published papers. So there's no worries there. Just let me know.
Okay, thank you, Turan. Yeah, that's very good. Thank you.
Thanks. And but by the way, Lucian, I'm trying this new software now, and I cannot see the chat window here.
I'll let you know. So Christopher asked, but he should send you an email.
Okay. Great. Yeah, today I had like two technical difficulties back to back, so I'm feeling a bit old, but
Well, it's happening, you know, the new technology.
yeah. Yeah. Um,
Yeah.
okay, though. So if you don't know anything about symmetry, you can still diagonalize this force constant matrix and sorry, dynamical matrix, the one on the right, get a bunch of numbers, and the square roots of those numbers would be your phonon frequencies. And if you, for example, are using VASP and you use one of its default ways to calculate phonon frequencies, that's exactly what these codes do. They either displace atoms one by one, which is called the frozen phonons approach, and calculate the forces, or they might be doing DFT. But most DFT codes do this in a way blind to the symmetry of the system. Not all, and sometimes symmetry is used to some extent. So like if you're a developer, please don't get offended. I'm like making overgeneralization here.
So if I understood correctly, so if you do one by one, you call frozen approximation, but then what's the other option?
So the other option is using density functional perturbation theory.
Okay.
So in VASP, that's I brine equal to 8. So it does a perturbative expansion. Its implementation is a bit tricky, so I'm not getting into the details. But there also, you need to consider specific perturbations to your system and calculate your system's response to that. And again, most of the time, the perturbations considered are just individual atomic displacements.
Okay, I see. Okay.
So that's the more brute force method that doesn't take advantage of the space group representations, for example. And for example, when you do it in VASP, and again, the reason that I'm using VASP is just as an example. I'm not saying it's the best code, or I'm not like pointing out, like I'm not advertising for it or anything in a way.
But there are many codes, yes. I mean, we can do this.
There are many codes, and their formats are usually like well, the output formats are different, but basically what you get is a list of phonon modes. And again, in barium you would end up with 15 phonon modes. I'm showing only 5 of them, which involve displacement along the z-axis. So each phonon mode in barium is threefold degenerate. You would have a x, one along x, one along y, one along z that are exactly the same. So as you see, I have on the 3rd, 5th, 9th, 12th, and 14th mode. And on the left, you have the coordinates of the atoms repeated. On the first line, you have the frequency given in various units. I like, spectroscopists report frequencies in reciprocal centimeters, which is a weird unit for a frequency. I know, but up to a factor of C, H bar or whatnot, reciprocal centimeter turns out to be the same thing as terahertz. And on the rightmost column, the 3 columns, you see dx, dy, dz. This is the displacement pattern of each phonon mode. So for example, if we look at this one, it looks like it involves only displacements along z, and the first atom, which is the barium, is displaced by very little. The second atom is displaced by a lot. This is the tin, and the last 3 atoms are oxygens. 2 of the last 2 oxygens are displaced by a lot, but the first oxygen isn't displaced by as much, and the oxygen displacement has the opposite sign as the titanium one. So
these are the displacements we have put in initially, or?
No, these are essentially the eigenvectors of the dynamical matrix now. So when you diagonalize this matrix, when you find the eigenvalues and eigenvectors of this dynamical matrix, you find these eigenvectors, which are these displacement patterns.
Yes, I see. Mm-hmm.
And then the eigenvalues square root, gives you the frequency. And there are quite a few factors of different units converting from electron volts per angstrom square per atomic mass unit to something in terahertz. So I find that starting students usually spend a good afternoon at least to get the units.
We spend the same.
Yeah. I was trying not to be too humble, but if you want me to get the units right, like I need a day for sure.
Yeah, it's okay. Thank you, Turan. Yeah. Mm-hmm.
Thank you. Now, what you can do is, if you are really interested about the details of these phonon modes, you can, okay, the screen seems to be frozen. Okay, yeah, there we go. You can, using a software like Vesta, and again, spending some manual labor until someone develops a code that does this automatically, you can you can sketch the displacement patterns of different phonons. Now, the first phonon, for example, involves a displacement of all atoms along the same direction. And there's a little subtlety here. Remember, the dynamical matrix is the force constant divided by the square root of masses, atomic masses. So the eigenvector of the dynamical matrix actually needs to be multiplied by the square root of the corresponding atom's mass to give you the displacement. So the first mod, even though it doesn't have equal magnitudes of dz here, this is what we call the acoustic mode when you take into account everything correctly, including the atomic masses. This corresponds to all the atoms moving along the same direction by the same amount. And the frequency of these acoustic modes, since they are just a translation of the whole crystal, is supposed to be zero. Here you see the frequency is very small. It is never exactly zero in DFT. You discretize the reciprocal space due to this using a finite K-grid. As a result, you don't have perfect translational symmetry in our calculations, and the acoustic modes are never at zero frequency. But the smaller these numbers are, the better. So this is a good measure of your quality of your calculation. And then there are these other modes which involve, for example, this next one involves all the cations. So the tin, which is in green, and the tin is in gray, and the baryons, which are in green, moving along the same direction as the oxygens, but in such a way that the baryons move, the first atom, against everything else. So the tin moves along together with the oxygens. So a mode like this would create a dipole moment, right? Because you have some net charge moving in one direction due to baryons against everything else. Then there's this third mode, for example, where the first three atoms don't move at all. It's just a pair of oxygens moving against each other. So it looks like this. So what I'm trying to convey here is, in this specific material, there's no reason for you to care about every individual phonon. But what I'm trying to convey here is that there are these different phonons with different characters, right? Like when you look at them, you can sort of distinguish their properties. And what can be done is, it turns out that you can assign a space group irrep. Irrep means irreducible representation, which I will just call representation from now on because we won't talk about reducible ones separately. You can assign a representation to each phonon mode that determines its characters, just like the different vibrational patterns of the carbon dioxide molecule we used before. The barium stenate crystal has different vibrational modes with different characters. So it turns out that out of the 5 modes, 4 of them are gamma 4 minus modes, and I will talk about how to assign these in a bit. And one of them is a gamma 5 minus mode. Now, gamma 4 minus representation turns out to be a representation that's polar, that is infrared active. And what we mean by that is this representation, these phonons, when you displace atoms according to that pattern, creates an electric dipole. And it is extremely important whether a phonon mode creates an electric dipole or not, because when you shine light on barium stenate, it's only these phonons that create an electric dipole, a vibrating electric dipole, that can absorb the light that you shine on the crystal. Similarly, there are other selection rules that determines whether, for example, you can see a phonon mode in Raman spectroscopy. And it turns out that this gamma 5 minus mode, the one where these oxygens are moving against each other, is a silent mode. Silent means that you cannot see it in infrared absorption, and you cannot see it in Raman scattering, which means that you have extremely limited experimental tools if you want to detect this gamma 5 minus mode. So, okay. So this already gives us a good bit of information about what experimental observations we may have. For example, when you shine, if you read experimental paper and they say detect 5 different phonon modes that absorb light shine onto them through first order processes, you can already get suspicious, right? Because, well, there's this one mode here that is not supposed to, this one, the gamma 5 minus 1, that is not supposed to absorb any light. And for first principles calculations, the good thing about this sort of approach is that, for example, you already know the displacement pattern of that silent mode, right? It's just two oxygens moving against each other. That's the sort of thing we could have actually guessed without doing a first principles calculation. And how we can do it, I'm going to tell you about now. Now, we can use symmetry, in particular the space group and the Wyckoff positions of the atoms, to predict the degeneracies of the phonons. So how many phonons you have for each representation and what's the degeneracy of these representations are without even doing DFT. So you can do this before doing DFT to guess what the outcome will be, or you can do this after doing DFT to confirm your result. So for this, there's a tool called SMODs, short for, I guess, symmetry adapted mode. Excuse me, symmetry adapted modes, again in the Isotrope software suite, which you can find in this web address. It's an extremely simple tool. Well, simple meaning learning the keywords, etc., takes a bit of time, but the tool itself, if you are using the web interface, is a single text box, which you fill and press OK. Okay. And the information you provide in this single text box for barium stenate, the compound that we talked about, is this. So there's the title line. In the second line, you specify the space group by its number. So it turns out to be 221 in this case. And this one you can find using FindSim, the tool that we discussed in the previous lecture. In the third line, you have the 3 lattice parameters and the angles between these lattice parameters. So this is a cubic system. So all 3 lattice parameters A, B, C are equal to each other, 4.11 in this case. And the angles between those lattice parameters are all 90 degrees. Again, this is the information that you can just use FindSim to give you in a similar format. There are 3 different Wyckoff sites occupied. And you might remember in our example, we found that barium is on the Wyckoff site A, tin is on the Wyckoff site B, and oxygen is in Wyckoff site C. And finally, I am interested in only a single wave vector, k is equal to 0 in particular. And that wave vector is called gamma, which we denote by GM. And the names of different points in the Brillouin zone, you know, there are these special names given to special high symmetry points in the Brillouin zone. Those we can also find in these Bilbao server or the international tables, which, well, in the next iteration of this course, I guess I will have a slide talking about that too. But anyway, so when I submit this input to SMODs, it is going to give me all the information that symmetry, that group theory can tell about the phonons of the system. It is not going to give me any frequencies, because for that I actually need to do DFT or an experimental measurement, but it will tell me the representations and the form of the atomic displacements for different phonon modes. Okay, so this is the output. This is all the output. And let's look at this both sides one by one and discuss them. So basically this says that at the k vector gamma, there's an irrep gamma 4 minus, and then there's an irrep gamma 5 minus, okay? And the left column is the information about the gamma 4 minus. So the name of the representation is given first. And again, there are 2 conventions actually. I like calling this gamma 4 minus, but there's this alternative convention where this would be called the T1U mode. It's a 3-fold degenerate mode. And this 3-fold degeneracy comes from the fact that you have a cubic crystal. So if you have a vibration pattern along X, there's a equivalent vibration pattern, symmetry equivalent pattern along Y or Z with exactly the same frequency. The total number of modes is 12, which means that there will be 4 separate sets of 3-fold degenerate modes. So I will end up with 4 different sets of gamma 4 minus modes. So remember that in the earlier slides, we saw actually 4 gamma 4 minus modes and 1 gamma 5 minus mode, right? So we were looking at only a single direction. So we ended up with 4 gamma 4 minus. Here this says these include 3 translational modes. So you might remember that there was that 0 frequency mode, which corresponds to the translation of the crystal. That's included in this list. It is infrared active. It creates a dipole. Here it gives us the coordinates of the atoms that I would need to calculate this type of a phonon in DFT. This is just a primitive unit cell. Since this is a gamma point mode, I didn't need a supercell. And here are the 4 different sets of displacements. So what this tells me is that for one of these threefold degenerate modes, for example, the one along, it looks like along X, I have barium displacements as 1 degree of freedom. I have tin displacements as another degree of freedom. Then I have the first oxygen displacement. And then I have the last 2 oxygens being displaced together. So this is, for example, a giveaway for gamma 4 minus. Essentially, every atom moves, but the last 2 oxygens, or 2 of the 3 oxygens, the order of the oxygens may change, of course, they move together by exactly the same amount. Now, let me go back to the output of my DFT calculation, a few slides back, and see if our gamma 4 minus mode obeys this. Indeed, up to numerical noise, it does. So, for example, when I look at this last one, which I claimed without proof at the time to be a gamma 4 minus mode, if you look carefully, the last 3 rows are oxygen displacements. The first oxygen moves by a different amount than the last 2, but the last 2 move up to some noise by the same amount. Same applies for the other gamma 4 minus modes too, so to this or to this as well. Here, the gamma 5 minus mode, it doesn't do the same thing. It has the 2 oxygens move in opposite directions, equal but opposite directions. So let's see if that is true for this is the gamma 5 minus mode, right? So let's see if this is true for the gamma 5 minus. So let's see if what S mode says. So again, this was gamma 4 minus, and this is gamma 5 minus. So what this tells me is that the gamma 5 minus representation gives rise to 1 threefold degenerate mode. So the degeneracy is 3 and the total number is 3. And then there is only 1 symmetry adapted displacement. This tells me, S modes tells me, which doesn't know about DFT, it didn't do a calculation on barium stanate itself, it doesn't know the electronic structure, it doesn't know the force constant, but it says that there will be this one phonon which only involves the displacements of 2 oxygens in opposite directions. Now, nowadays we have more computational power than our advisors back in early 2000s or 1990s. So it's not too expensive to do a phonon calculation, even when you have 40, 50 atoms in a unit cell, if you are using DFT. If you are using something like dynamical mean field theory and more advanced electronic structure method, of course, computational power can be an issue. But when we have limited computational power, we might not want to calculate all the phonons together. So if for some reason I was interested only in this gamma 5 minus mode. So if I was only interested in this specific mode, I didn't need to calculate the whole 5 by 5 dynamical matrix. I could just perform one displacement of atoms. And when you do a displacement where you displace these 2 oxygens in opposite directions, the force will be only along the same direction as well. So you will only end up with a force that will be along the same displacement, and you can just take the square root of that force. You can divide that force with the mass of the oxygen and take the square root, and that will give you the frequency of this gamma 5 minus mode. So in other words, in the case of a perovskite, you have this 5 by 5 dynamical matrix, but this representation is actually enable you to write it as a 4 by 4 block and a 1 by 1 block. And if you're only interested in that 1 by 1 block that corresponds to gamma 5 minus, that's all you need to calculate from first principles. Now,
sorry, Turan, before you go forward, can I have another question? Sorry. So here for the atom 3 and 5, symmetry tells you that, so what I want to understand is you have 0, 0, -1 and 0, 0, 1. So basically, this tells me that these two atoms, by symmetry, they can only move along the z-axis in opposite directions.
For this phonon mode.
For this phonon mode. So, and then if you go back to the other gamma 4 minus, so here in principle, I have this, I mean, there is no displacement along x, y and z, it's just x.
Yeah, yeah. The confusing thing about this tool is, so you have for each phonon, you have one polarized along x, one along y, one along z. This
Because the
includes
symmetry.
one of them.
Yeah, it's
So
a symmetry. And yes, of course, I can have the same thing in any direction, x, y, z. Okay, see, I get the point. And then
correct.
you also mentioned that here by symmetry, 4 or 5 have to have the same displacement.
Correct.
But in principle, this tells me that, for example, barium, Sn, and oxygen, they can have different values because this gives me gamma 4 how it looks. But if you look at your DFT calculation, you have 4 gamma 4s. The
Yes.
only difference between those 4 is the displacements.
Right. So you take a superposition of these 4 symmetry adapted modes, and when you have these 4 independent, linearly independent displacement patterns, you can end up with 4 linearly independent eigenvectors of the dynamic matrix. So yeah, you multiply these with 4 arbitrary numbers, and the combination would be an eigenvector, right?
Yeah, okay, I see. Okay, thank you.
Now, one question that might pop up in your head as well, why would I ever care about a single phonon mode? Because you know, when people publish papers, very often, like, you calculate a bunch of properties of a specific material you are working on, and the phonon frequencies is just one that you report. But there are specific situations where you would care only about a specific phonon or a specific group of phonons. So, for example, we had a recent paper where we worked with an experimentalist who measured the Raman spectrum of a specific material, in which case there are only two, and we had a huge unit cell. It was a very noisy material, like it was metallic, there was possible spin-orbit coupling, the structure is not well converged. So there were a lot of headaches in DFT, and but we were only interested in the Raman active modes, because that was what the experiment was about. So in such a case, it's better to use this type of approach and calculate only as a small part of the whole dynamical matrix, because this way you get less noise, right? Because there's, you know, when you do a calculation, you always get these like off-diagonal elements, which are supposed to be 0. They come out as non-zero. They are small, but nevertheless non-zero, so they affect the quality of your results. If you do this, if you just calculate the symmetry adapted modes for a specific block of the dynamical matrix, you get rid of that error. And then the other positive thing is, again, if you have a large unit cell, in our case, I think the unit cell was 40 atoms or something, where again, it was a metal, so convergence was an issue, where the computations was somewhat expensive, and you know, it was a material where there was a pressure to publish quickly, especially from our experimentals colleagues. So this actually proved to be a fruitful approach. It saved us quite a bit of time.
But why is it more difficult for metals than insulators?
So if you have an insulator, when you are trying to achieve convergence as a function of the number of K points you use in your DFT calculation, so the K grid, these forces are very hard to converge because these are technically spatial derivatives, so they need a very fine K point mesh. When you have an insulator, convergence is easier to achieve. When you have a metal, in practice, you need many more K points to get the same quality of forces. So,
I see. Okay.
from the point of view of phonons, a metal or an insulator doesn't matter. You know, we just care about the electronic displacement.
Yes, I see. But it's the convergence you're saying.
Yeah, converging a metal in practice is much harder. And this was a specific type of metal which had a possible firm surface instability, so it was extra hard.
Okay. Yes, I see.
Just the type of material that I don't know, that is scientifically exciting, but not very pleasurable to work with, I guess.
Yeah, I know the feeling. Thank you.
Oh, yeah. Thanks. Okay. The other place where you might be interested in only a small number of phonons in a specific material is when the material has a structural phase transition. So, in elementary school, we learn about the three phases of matters, right? Liquid, gas, solid. But then even in the solid phase, many materials display many solid to solid phase transitions where either the electronic or the crystal structure changes. So you might get the crystal structure and the space group change spontaneously below a certain temperature. And it is traditionally the way to understand these phase transitions is again using phonons as a basis to expand the displacements of the atoms in the crystal. Okay. So for example, there is barium titanate, which is a so-called ferroelectric. Now, barium titanate is a perovskite. It's an insulator. Electronic structure, again, like a vegetable. It's a wide bandgap insulator. There's no magnetism. There's no like firm surface or any related effect. And about 400 Kelvin, it's nicely cubic. But when you do a density functional theory calculation, you predict a phonon with an imaginary frequency. So density functional theory works at zero temperature, right? And it predicts phonon frequencies to be either real and positive or imaginary. And when they are imaginary, we often plot them as negative in the dispersion plots just because like it's a convenient way to plot them. But those imaginary phonon frequencies correspond to structural instabilities. In particular, consider the figure on the left. Let's say we have the energy of our system as a function of the displacement of one or more atoms according to some like specific phonon displacement pattern. Now, the energy of a mass on a spring, which is how you can like imagine a phonon in a very simple term, is 1/2 kx squared. So in this situation, the second derivative of energy at zero, which is your force constant, is positive, right? So k, the force constant, is positive. Your omega square is positive. The square root of a positive real number is a positive real number. So you end up with a phonon frequency that's just like 5 terahertz, some positive real number. But if you were to have an energy landscape that looks like this, that had this double well shape, and if you were to calculate the phonon frequency for the system where the phonon displacement is zero, this is where you have a structural instability. This is when you displace an atom, say, by a little bit to the right, that atom would spontaneously roll down from this hill, and the system will actually be happier, meaning the system will have a lower energy at low temperature in the bottom of this well, where the phonon displacements are frozen in now. So when you calculate the phonons at the center, the second derivative of energy here is negative. So omega squared, the frequency squared, the dynamical matrix eigenvalue or force constant matrix eigenvalue is negative, which gives you an imaginary frequency omega. So it's typical now to perform DFT calculations in systems. And when you find an imaginary phonon frequency, you say that, aha, the structure I have might be physically reasonable, like barium titanate could be cubic at some high temperature. But when I do the calculation at zero temperature, I find this structure to be unstable. These atoms want to displace spontaneously. And indeed, this is in line with the experiment. What happens in barium titanate is that this titanium atom in the center of the unit cell spontaneously displaces towards one side of the cube, let's say along the z direction, below 400 Kelvin. And when all titanium atoms in the unit cell do this in a coherent fashion, you end up with a net positive charge accumulation on the top surface of your crystal that gives rise to a macroscopic dipole moment in barium titanate. So materials which develop a macroscopic dipole moment that you can also switch by applying an external electric field are called ferroelectrics. They are very interesting materials. They were originally discovered in 1921 in the University of Minnesota, just across the street from my office. And now they have tremendous technological applications. So I suppose some of you at least will have very bright and rich futures developing new ferroelectric materials for example, memory applications. And what you see when you do a phonon calculation in barium titanate is an unstable gamma 4 minus phonon, which has a very heavy contribution from titanium displacements against oxygens. It looks exactly like this. So when you do the DFT calculation, you see that there's this instability where the first row is barium displacement, it's tiny. Second row is titanium displacement, it's in minus z direction. And the last three rows are oxygen displacements. Again, the last two oxygens are displaced by equal amounts. This is a clearly gamma 4 minus mode. The frequency turns out to be 195 times I reciprocal centimeter or 5.85 I terahertz. Though this is not a vibrational mode anymore, right? This is an unstable mode. So the frequency is somewhat not too meaningful. And I don't know what the imaginary frequency is like anyway. Some people think of this as like a damped oscillator, which is not a good analogy. And the nature of this mode, gamma 4 minus mode, determines the nature of the phase transition here. In particular, I told you that this gamma 4 minus mode is a infrared active mode or a polar mode, which creates an electric dipole moment. This is why at the low temperature structure of barium titanate, you end up with this macroscopic dipole moment. If this wasn't a gamma 4 minus mode, like if this was the gamma 5 minus mode where you have the oxygens moving opposite directions, that wouldn't lead to a macroscopic dipole moment in barium titanate, and hence it wouldn't be a ferroelectric. It would be just another boring compound that has some structural transition that has zero technological importance. Okay. And yeah, so this is what the displacement pattern looks like mostly. Okay. Now, I know that the space group of barium titanate is PM3 bar M, number 221 at high temperature. We have seen the perovskite structure, cubic perovskite structure. We plugged it in that FindSim tool earlier in the morning. But at low temperature, since there are these atomic displacements, some symmetries must be broken. And most importantly, for example, inversion symmetry is broken. In the cubic perovskite structure, you can invert the whole crystal structure around the atom in the center, and the structure would remain invariant. But when this titanium atom is displaced along plus z direction, for example, when you invert the structure, it goes to the negative direction, right? So clearly the structure is not invariant. There is no inversion symmetry anymore. So the name of the space group must change. But what could the new space group be? And this is an important thing to check in beforehand, because there will be cases like in the time permitting, I will tell you about our recent work on some Kagome compounds, where there are just too many options that you don't want to try one by just like randomly displacing atoms. So it's good to have some good starting guess about the possible distinct low symmetry structures. And also experimentally, if you have a friend or a colleague who is going to do X-ray diffraction in barium titanate at low temperature to figure out what the crystal structure is, they would really like it if you give them some possibilities of structures, so that when they do their Rietveld refinement or whatever other method they use to get the crystal structure from the X-ray diffraction data, they have some guidance. Okay, so the states of what our knowledge is that we know there are some atomic displacements that are unstable, that freeze in at lower temperature, that correspond to a ferroelectric phase, a ferroelectric polarization. We know that the order parameter of this polarization is, of this transition, is the polarization, is the gamma 4 minus phonon mode. So it is, if you have taken statistical physics, you might remember this idea of an order parameter that defines the properties of a phase transition. Like in a magnetic transition, it would be a magnetization, for example. Here, it is the polarization, or equivalently, it's this gamma 4 minus mode. Now, we can predict the possible low symmetry structures, the complete list of unique, distinct low symmetry structures, using just symmetry, just this knowledge, using a tool called isotropy, which is the command line version of that isotropy software suite, okay? Which again is just a text box with a submit input button on the bottom. Okay, so here's the input that I give. So what I tell is that I start from the parent space group 221. This is the number of the cubic perovskite space group. I have the irreducible representation. Representation, this is just the alternative word, irrep for now, is gamma 4 minus. And I ask the code to show me the subgroups and show me the direction vectors in those subgroups of my irreducible representation. And display ISO is just the last line saying, okay, I'm done giving you inputs, give me the result now. So you type these and press submit inputs. You end up with this list. This is a list of 6 different space groups. So number 99 is P4MM, number 38 is AMM2, etc. That can be the low symmetry space groups of barium titanate. So if your polarization, if your atomic displacements along A00 direction, so if they're along the x-axis, you end up with space group P4MM, apparently. Y and Z axes are not separately listed because they would give rise to the same space group, so we don't need that knowledge. If you displace the titanium along the 110 axis, for example, you end up with AMM2. If you displace it along AAA 111 axis of your crystal, you end up with the rhombohedral R3M structure, and so on and so forth. So when I observe barium titanates, when I know that there is a gamma 4 minus instability, what I know without doing the XRD is that the low temperature structure must be one of these. Okay, and this, by the way, also gives you a summary of the input in the beginning, just in case you forget it in the 10 seconds between you press the button and finish reading the results. Now, what you can always do is, if you don't trust group theory or don't take my word, which you should never, right? You should test the predictions yourself. You can take a cubic perovskite. You can displace the titanium atom in the center along these different directions, and you can put that structure into the FindSim tool. And what you will see is that that FindSim will give you the same space groups that you predict using this isotropic software suite. But again, isotropic software suite doesn't know about the details of your crystal structure. You just told it the parent space group and the irrep, the representation that the phonon responsible of the phase transition transforms as. I know we are mostly theorists, but experimental what happens is that at 400 Kelvin, the phase transition happens from the PM3 bar M, so number 221, to this space group, P4MM. So that part is consistent with our theory. And as you reduce the temperature, actually, there is another transition to number 38, AMM2, and then there's another transition at lower temperature to R3M, 160. So barium titanate has a very rich phase diagram, it turns out. Okay, so as I said, you can just change the crystal structure. So these are, again, VASP input files. What I did is I just take the starting structure, which was cubic, and then displace the titanium atom along the Z direction, or for the center one along X plus Y, or for the last one along X plus Y plus Z. And when I relax these structures now, right? So you can put these structures in FindSim, and you should put these structures in FindSim to confirm their space groups. But when you relax them, you will see that other atoms are also displaced according to the displacement pattern of this phonon displacement you started with. And even though I start only with the titanium displacement, my gamma 4 minus also involved, I don't know if this is too small to read, but I think I can read it if I a bit get close to the screen and squint my eyes. It's not only the titanium that's displaced, but the barium is also displaced. And the 3 oxygens are also displaced, but notice that the last 2 ones, for example, are displaced by equal amounts. So the resultant pattern preserves the symmetry, and hence it preserves some features of that original phonon mode that we found to be unstable, the gamma 4 minus mode. And when you do these relaxations, these different structures will give you different energies. And compared to the high symmetry, the cubic structure, this structure with polarization along the z-axis has an energy that's 19.9 millielectron volts lower This middle one is lower by 24.9 millielectron volts, and the last one is lower by 26.5 millielectron volts. Now, these numbers are actually important. So these are all zero temperature results. That's where DFT works. But these numbers are nevertheless important, even though you cannot directly compare them with the temperature, like just face to face. Now, room temperature, KBT, sets the energy scale of 25.8 millielectron volts, right? So I think this is a number that we should all know, maybe not three significant figures, but 25 millielectron volts is the room temperature. That's important because if the room temperature energy scale was, like, say, much higher than the typical covalent bond energy scale, we wouldn't have any covalent bond solids in nature, right? So what that temperature scale means, what that energy scale means in this context, however, is that temperature is comparable to the energy gain of barium titanate due to this polar displacement, these ferroelectric displacements. So what this tells me is I cannot make very solid predictions because, again, this is a zero temperature calculation. But I won't be too surprised that if I increase the temperature well above the room temperature, due to the entropy, essentially just due to the temperature, right, KBT, I will have so much disturbance in my system that this ferroelectric displacement, this coherent displacement, will disappear, and I will have a cubic crystal structure, which is what's observed. And as I reduce the temperature around 0 Kelvin, the most likely candidate for the structural ground state is the one with the lowest energy, which turns out to be the experimental observation, this R3C, structure. And as you reduce the temperature, it turns out in this specific case that you go from PM3 bar M, the cubic structure, to this one first, and then to this one, and then finally to the one on the right, as you reduce the temperature and entropy becomes less and less important. Okay, and again, this is the observed order of transitions in the experiment.
One question before we go forward, sorry. Why do you just take Titan when you use the isotropy, the software, the order parameter just gives you the amplitude for titanium, but not why is just that atom picked? I missed that one somehow.
That's a great question. You don't have to just use titanium. So the thing is, the real phonon displacement pattern.
Here, yes, here.
Yeah, here. This has this has 5 atoms moving. So you could ideally just copy and paste this and add this displacement to the positions of the atoms and use that in FindSim and use that to start your relaxation. I just use titanium because titanium turns out to be the largest displacement and it was sufficient to break the symmetry.
Yes, but now when you go to the symmetry part, if you go next slide, next. So next, see, so here I did not understand this order parameter, A, B.
So this order parameter here doesn't know about titanium or barium, right? So the input I gave is only within this box. So this just says that I have some structure with symmetry 2 to 1. It doesn't even know that if it's a perovskite. And then it says that, okay, the order parameter is gamma 4 minus because the phonon mode under question was a gamma 4 minus phonon.
That you saw from the negative frequency in principle.
Correct. Yes.
Okay.
So
okay.
This would work. This result would be valid for any crystal structure with the space group 221 and the unstable mode gamma 4 minus. So whether that phonon displacement involves only titaniums or all the atoms in the unit cell, that doesn't change the symmetry. And I think that becomes a bit more evident when you compare the input file to a relaxation and the relaxed crystal structure. Like, even though I displace only titanium to begin with, all the atoms are displaced when I optimize the forces, when I relax the atomic positions.
Okay, I see. But what's the meaning of A, B, C? If you go back to that somehow is not clear. The notation.
In this specific case, A00 means a displacement along X, or Y or Z, so along a single cubic axis. AA0 means a displacement along a diagonal, so along x plus
Oh, I see. So
this.
you are allowed to have, but they have to be equal. If you go in X, you go in Y.
Correct.
And then I see. Okay, thank you. Yeah, okay, it's clear now.
So, for example, when you have a displacement along x and y by equal amounts, you end up with this space group AMM2.
Yes.
But if they are by unequal amounts, you end up with a much lower symmetry space group, just P. Yeah.
And this A is like a vector displacement of all the atoms, different amounts. But for example, if I go to 38, if I displaced all the atom by some vector for all the atoms, if I do in the X, I should do the same in the Y because
Correct.
they are A. Okay, thank you. I see.
Correct.
Thank you.
Correct. And when you are trying to take into account all the atoms at the same time, things get a bit tricky. So this is why
Yeah, I agree. Yes.
just placing the central atom in perovskites and then let DFT handle the rest. But it's
No, it's very good. I think it's very. I mean, you learn a lot if you do this kind of thing, especially if you have like your own material you want to study.
Yeah.
Thank you.
I mean, we are mostly talking about crystal structure here, but there are many cases where these types of structural transitions are triggered by something that the electrons are doing. Like there are Lucian, you would be familiar with, for example, the nickelates and so on, right? Like there are some on-site electronic structural changes on transition metals, which trigger crystal structural changes and so on. And getting the symmetry of the phonons right in such cases turn out to be very important. Okay, okay, I have about half an hour. The other thing you can do once you know the representation of unstable phonon, and that gives rise to a structural phase transition, is to write the Landau free energy for it. So again, if you are taking a thermodynamics statistical physics course, you might be familiar with this idea. So Landau came up with this idea that whenever you have a whenever you have a phase transition, not a structural phase transition, in general, there is something called an order parameter that determines the symmetry and nature of the phase transition. If you have a ferromagnet, your order parameter is the magnetization. It breaks the rotational symmetry in space as well as time reversal symmetry. If you have a ferroelectric transition, your order parameter would be either the gamma 4 minus phonon mode or polarization that determines how the inversion symmetry is broken. In things like liquid solid phase transitions, you can also define some correlation functions as your order parameters. Now, what we learn when we learn about first order versus second order phase transitions in this Landau paradigm is that you can write a free energy expansion as a polynomial, a low order polynomial of this order parameter, and the allowed terms determine what type of phase transition you have. So for example, if, as we have on the left here, you have a free energy that is a second order polynomial, and as you decrease the temperature, this alpha at high temperature is positive, but as you reduce the temperature, it becomes negative. Then there is a second order phase transition. So at high temperature, when you plot this f for beta is always considered positive. So as you plot this f for positive alpha, you have a single parabola with 0 at m is equal to 0. But as alpha crosses 0 and becomes negative, then the minimum of this potential will be at some non-zero value of alpha. These for a ferromagnet, for example, would be the points where you have a non-zero magnetization. Or for barium titanate, these are points where all the atoms are displaced along one direction or the opposite direction. Now, this is what we call a second order phase transition that has specific thermodynamic properties. But there are also situations, not as often in ferromagnets, but in other systems, where a cubic term is also allowed in the Landau free energy expansion. When you have this, you necessarily end up with a first order transition, and the condition is actually a bit more lax than even alpha being negative, but as you reduce the temperature and the second order coefficient becomes small as it gets close to 0, at one point you will end up with a minimum of your energy, free energy, on the negative side. And in this case, you will have an abrupt phase transition where the value of your order parameter does not increase continuously, but instead it just jumps from 0 to a finite and typically large value. So, can we say something about the ferroelectric phase transition of barium titanate? Is it a necessarily first order transition? Can it be a second order transition? And would this match with the experiment? It turns out the answer is yes. It turns out that once you know the representation of your order parameter, in our case, the representation is gamma 4 minus, right? Because it is what this unstable phonon is. Then you can actually write the full lambda free energy and then study it as a function of temperature. Now, if you want to consider polarization, which is that gamma 4 minus, what the gamma 4 minus mode gives rise to, it has three components, right? So it can be along X, Y, Z, or some superposition of them. So it's a three-dimensional order parameter, which we now need to take into account carefully. Okay, and one thing I should say about this polarization or gamma 4 minus is it is really just a vector. So, we learn about vectors in different levels and we develop different definitions. There are axial vectors, polar vectors, whatnot. The polar vector, what we shortly just call vector, is really just a gamma 4 minus in a cubic system. So it is a specific representation of the point group or the space group, okay? And the way to see this is when you look at the polarization, it does transform as a vector under all space group operations. But anyway, so let me skip ahead and tell you about a tool called invariance. So I want to find the lambda free energy that is a function of this polarization, which is a vector. So there's a formal way to do this using some like representations, higher powers and projections and whatnot. But essentially what we are just doing is we find all combinations of the gamma 4 minus, which is the polarization along XYZ, that are invariant under the space group symmetry operations. So there's a tool called invariance, which allows us to do this rather easily. The math behind this involves a lot of matrix products and sums and so on. So it's the type of thing that you give to a first-year grad student to see how patient you are, I guess. But it's really not something that's fun to do for human beings. So we use computers for this. Okay, so this tool is hosted in the Isotrope software suite, so you can access it from their main page. Again, this is the address for this specific tool, or there's a link to the invariance, Isotrope software in one of my earlier slides. So you start by choosing the space group, and our space group is 221, and we want to work with a single representation, so we choose only one superposed representation. You can work with multiple representations at the same time. There will be an example about that later on. You choose the K point of your representation. Our representation is at 0 wave vector at gamma. So I choose gamma here. Click next. I choose the irreducible representation itself. The representation is gamma 4 minus. So there's a drop-down menu. There are typically, depending on the space group, 3, 4 to maybe 10, 12 representations available. So ours is gamma 4 minus. You pick a general direction to be ABC. So I want to see the most general form where polarization along X, which is A, or polarization along Y, which is B, or along Z, which is C, can be non-zero and they can be different from each other. And just click next here. I want to go up to 4th order. And here is the result. So let me translate this a bit. The code tells me that the gamma 4 minus has 3 components A, B, C. These are the polarization along X, Y, and Z directions. And the lambda free energy expansion would have these different terms as distinct terms in the expansion. These are invariant polynomials. So if you have a cubic crystal, before it becomes polar, any of these terms would remain invariant under all the symmetry operations of that cubic crystal. So there's this first term, a square plus b square plus c square, which is this term in the free energy. So it's some constant alpha, we don't know what this number is, times px square plus py square plus pz square. And then at the 4th order, there are 2 different terms. There's this term, and then there's this term, which you can write as this with some unknown coefficient beta, px square plus py square plus pz square square. plus some other coefficient gamma times the fourth orders. So up to fourth order, this is all there is to the free energy of barium titanate. What this tells me is that there's nothing that is third order. So there's no cubic term. So this wouldn't fit with that stereotypical first order phase transition scenario that you read in the textbooks, for example. Now, these alpha, beta, gamma are unknown coefficients. They depend on the system. So this form of the free energy is valid for any perovskite, because any perovskite has a polar mode that transforms as gamma 4 minus and starts from the 2 to 1 space group. Now, the coefficients might be different, well, will be necessarily different from one material to the other, and that will give rise to possible structural instabilities. Some materials will be ferroelectric, some will not, and so on. So these Greek letter coefficients are material specific, and you can either obtain them from DFT or fit them to experimental observations. Nowadays, we do this from DFT regularly. Back in the day, especially, there was an art of figuring out what these coefficients could be with error bars on them, depending on the experimental observations. Like you can make guesses. Alpha corresponds to the phonon frequency squared. Some combination of alpha and beta gives you like a dielectric susceptibility and so on. So there were people who were experts on this, but nowadays, I think, in my opinion, it's mostly first principles art now. So these phases that the isotropy software suite told us could be the possible ground states, possible low energy structures, are all possible minima of this expansion. So for example, in order to have any three of these, any one of these technically, you need alpha to be negative. Otherwise, there will be no reason for P to become non-zero and break the symmetry to begin with. When you go down here, for example, when you look at the P1 space group, number 1, this is for a polarization along ABC. So this is a situation where you have polarization non-zero along all three cubic axes, but the magnitudes are all different. So a fourth order polynomial doesn't have a local minimum. Whatever coefficients you have, that would give you this phase. So typically these really low symmetry phases requires you to work with higher order free energy expansion. So you need to, if there's an experimental observation and the space group turns out to be P1 or even CM at low temperature, you really need to go back to invariance and write down the free energy, not up to fourth order, but maybe to sixth order or sometimes even eighth order. Okay. Another thing that might become important is other degrees of freedom that couple with your primary order parameter. So we know that the instability we have is gamma 4 minus, but typically when you have a structural phase transition, the shape and size of your unit cell also changes. So in this specific case, in the case of barium titanate, the strain, eta, couples with the polarization, with this gamma 4 minus order parameter. So eta, if you study the details, which unfortunately we cannot get into in the last 19 minutes we have, transform as a gamma 3 plus order parameter. So what we need to do is to write a Landau free energy expansion that both has gamma 4 minus, our polarization, and this gamma 3 plus, the strain. And when you do that, you can go back to invariance, introduce two order parameters, and ask for the expansion. It gets lengthy, things get tedious fairly quickly, but you end up with this expression where, as you see, there are also terms which couple the polarization squared with a certain combination of strains. And the first part of the free energy where you only have the polarization was easy to guess. Like in a cubic system, you can somewhat make an educated guess about like what type of second or fourth order terms you would have. But this coupling between strain and polarization is quite non-trivial, and it's not obvious what these cross terms would look like. Say, I don't know where the square root of 3 comes from, for example. So those are things that come out naturally from group theory calculations. And if you are into looking into details of structural transitions, where you have multiple different phonon modes that are involved, which is often the case, then you really need to figure out the allowed coupling terms between these different phonon modes, different order parameters, and using these symmetry tools really allow you to do that. Okay, now I want to tell you about some of my recent research. Unfortunately, I have only 17 minutes left, and I have another full hour of material here. So I'm going to skip ahead and just tell you about some results and something that we did from density functional theory using these lambda free energy expansions. And this is a material, it's cesium, vanadium-3, and 25 in particular. These are a group of Kagome metals, which have been the focus of very intense research for the last couple of years. I was expecting these materials to be like competing with twisted bilayer graphene actually in this year's March meeting, but then there was this claim of room temperature superconductivity, which just took all the time of all the discussions. So we didn't hear as much about Kagomes, but still there were like 100 talks about them. But so these are very exciting materials of like active research interest now. But before I jump into that, are there any questions? And I can't see the chat box. So if there's anything in the chat box, could someone yell at me? No?
Hi, I have a question.
Sure.
So you mentioned that we need to use the unstable phonon and its representation in the input where we were trying to find the lower symmetry space group. So it seems like this is an example of like the order parameter breaking the symmetry.
Correct.
But you explained that and normally how I understand that is that the order parameter no longer transforms as an identity under the entire group, but you phrased it as seeing the order parameter transforming under a particular irrep. Do you think you could maybe unpack that a little bit?
Sure, of course. So when I talk about the representations, I specifically refer to the representations of the parent space group, where the order parameter transforms as some irrep, which is gamma 4 minus now. Now, once the order parameter actually freezes in and the symmetry is reduced, you can then again do the group theory analysis in that low symmetry structure and find a new representation name for the order parameter. Now it would be the representation of that low symmetry space group. And since the order parameter breaks all the relevant symmetries, then it always becomes the identity representation. So it becomes A1G of the low symmetry space group. So if you were a spectroscopist and you were talking about a transition, for example, the order parameter of that transition always becomes A1G or gamma 1 plus, the trivial representation, so-called, below the transition. And again, say Raman people really like this. This is how they understand the degrees of atomic displacements and so on. But when we are talking about, like when we are writing the free energy expansion and so on, we need a starting point and we need to keep that starting point consistent. So we always use the representations of the high symmetry space group, the high temperature, the reference space group. Does that answer your question?
Yeah, that answers that perfectly. And just to confirm, once we find the lower symmetry group, we expect that to respect the order parameter, albeit maybe in a trivial fashion. That was sort of what you concluded?
Sure. I mean, so what defines a representation is how the order parameter changes under at least some of the symmetry operations of the group. In the low symmetry structure, there is no more any operation that can change the order parameter. So this is what I meant by trivial.
Okay, yeah, that makes a lot of sense. Thank you.
And I think trivial there is even the technical term in group theory, though I'm not a mathematician, so I'm not an expert. So it wasn't like I'm not discriminating against any representation or anything. So, okay, other questions? All right. All right, so let me move on in 10 minutes through 1 hour of material, which is always exciting, right? So anyway. So the structure I'm going to tell you about is this structure for Kagome metals, cesium, vanadium-3, and 25. Cesium is the light blue atoms, and it's really not important here. It's the vanadium layer that seems to be exciting. Vanadiums form this so-called Kagome lattice. The space group is P6/MMM. And if you are into things like frustrated magnetism, this Kagome lattice is pretty famous already, right? It's a specific pattern of corner sharing triangles, essentially. Now, it turns out that there's a structural phase transition in the system at 94 Kelvin, and you can see it in the specific heats on the right, in resistivity, and as well as magnetic susceptibility. And there is also at really low temperature, at 2 point something Kelvin, superconductivity observed with possible topological aspects. So there's a lot of like fancy correlated electron physics going on somewhere at low temperature. But I am interested in this talk at this 94 Kelvin transition where the crystal structure changes. But we aren't sure, well, at the time that we started this research, we weren't sure what the exact changes. Okay. In particular, experimentally, people could not differentiate between two different patterns. So it looked like vanadium atoms drive this transition. So it's a so-called charge density wave transition, where the electrons actually spontaneously want to break the translational symmetry and force the atoms to displace in specific forms. And below 94 Kelvin, some vanadium atoms get closer to each other to form some closed loop bond patterns. And those bond patterns were discussed to be either Star of David or the trihexagonal pattern, but it turns out that these give rise to extremely similar X-ray diffraction results, and therefore there wasn't an experimental resolution at the time about what the low temperature crystal structure is. So this is where we came in. So when we started, there were already some phonon dispersion calculations in these systems, and people had this data. So this is a unit cell with 9 atoms. Therefore, you end up with 27 phonon branches. This is why you end up with this spaghetti plot. What was displaced on the negative axis here are the imaginary phonon modes, where you see that there's an instability at the M point and there's another one at the L point. So this is the shape of the Brillouin zone. These are where the M and L points are. There are 3 distinct M points, 3 distinct L points in the star of these wave vectors. So there were overall 6 distinct instabilities. And these are instabilities with non-zero wave vector. They are at the zone boundary. And as a result, what I have told you so far for the gamma point was somewhat easier than to deal with this system where we are not at the gamma point anymore. Okay. So if you take a superposition of the 3 M point instabilities, which I show in red, blue, and green arrows here, when you have an equal superposition, you form this trihexagonal pattern, it turns out. And when you flip just one of the 3, however, so if you flip, for example, just red arrows, then you end up with these stars of David. So it turns out that both phases that people were arguing about are actually induced by the same phonon instability. And the difference between M and L is that L also has an autoplane component, so it would give rise to this autoplane modulation. So you wouldn't end up with the same pattern on each Kagome layer, but instead neighboring Kagome layers could have different structures. Now, what you could do is, without using even much group theory, you can take the unstable displacement patterns from DFT, and by superposing them, you could build different structures and you could relax these structures one by one to figure out what their energies are. And presumably the lowest energy structure should be the structural ground state, right? So this was already done when we started working on this in like 2021 or so, in the middle of COVID. And it turns out, however, is that there are simply too many options you can imagine. So for example, if you forget about the L phonon and just consider M, you can end up with, depending on the signs, either Star of David or trihexagonal patterns on each Kagome layer. These are just the vanadium atoms I'm showing for simplicity. But if you have all L's, then you can end up with alternating Star of David or trihexagonal layers, and we call them superposed because the bond lengths are not quite equal. But also you can have 2 components of L and 1 component of M to be non-zero, and depending on the signs you can get these staggered patterns where you have either trihexagonals or Stars of David, where the centers are staggered from one layer to the other. Each of these give rise to different space groups. Sometimes coincidental, the space groups match. And there just seems to be too many of these to try and find by trial and error. So we want to make sure when we start doing this, being, somewhat experts in group theory, to make sure that we have considered all the structures that one can possibly obtain by these two phonon instabilities. For that, we use the space group representations. We know that from DFT, we know that the M point phonon is M1 plus and L point phonon is L2 minus representation of the space groups. Then we used isotropy, just as we did for barium titanate in this talk, to figure out all the possible low symmetry structures. So we ended up with a list of 17 different symmetries here, many of which actually overlap. For example, you have this 191 here with M and L, which is exactly the same thing as this 191 here. So when you get rid of that double counted ones, there were 12 distinct low symmetry phases. So if you were to do 12 different DFT calculations with 12 different symmetries, in principle, you should be able to get all the different possible low symmetry structures. Now, but it's not clear if all of these are equally likely, right? Because remember that in barium titanate, we had a fourth order expansion. And I said that the fourth order expansion wouldn't give you those like really low symmetry space groups, right? So similarly, a fourth order expansion here probably wouldn't lead to P2/M, this really low symmetry space group. So probably not all of these are metastable, right? So can we be sure how like some are more likely than the others? So for that, we write the free energy expansion, which turns out to be this little monster here with so many different terms. So you can write it as a sum of three terms, one with just M, Fm, one with just L, and then there are these cross terms. This one actually has third order terms as well, but special third order terms, which were not just M cubed, for example, but the three components of M multiplying each other. These are called trilinear terms. If you are into ferroelectricity, hybrid improper ferroelectricity comes from a similar trilinear term. And there are also trilinear terms between M and L, so M1, L2, L3. Now, this free energy expansion is complicated in itself, and it has a lot of coefficients. But you can use DFT to calculate these coefficients, and that's what we did. So if you just consider the M part, the phase diagram is rather simple. So there are only three phases that are possible. This one you can just do by like guessing the coefficients here and then changing them as a function of temperature. But we can get these coefficients from DFT as well. In particular, for that free energy, you have 3 degrees of freedom, M1, M2, M3. You can do a DFT calculation for different amplitudes of M1, which is the horizontal axis, and different amplitudes of M2. And at each grid point here, for frozen structure, no relaxation, calculate the energy from DFT and plot it. It gives you this minimum, this energy landscape. So if M1 and M2 were your only degrees of freedom, your minimum energy structure would be here. But you also have M3, and the relative sign of M1 with respect to M2 and M3 matters. So you should also do a calculation where the vertical axis is M2, M3 together, equal to each other. Horizontal axis is M1. In this structure, you have the trihexagonal structure here, which is the minimum of energy. And you have the Star of David structure here, where there is a local minimum, which is very faint, so you can't quite see it. Now, when you have L as well, you have that monstrous free energy expansion. So things get tricky. And you need to consider multiple different cuts in the 6-dimensional phase space where you have M1, M2, M3, as well as L1, L2, L3 as order parameters. So this is what we did. I had a postdoc, Ethan, who is starting a faculty job in Harvey Mudd next month. And what he did is he performed DFT calculations, what you see on the bottom row, as a function of L and M order parameters along different planes of the phase space. And he fitted the coefficients of that monstrous Landau free energy expansion to the energy he obtained here. And those fits give rise to the plots in the top, which look not perfectly identical, which they shouldn't be, right? Because we cut the free energy expansion at the fourth order. In principle, it's the infinite order polynomial, but qualitatively, they are the same. It has the correct minima in the correct places with the correct order of energies. So what this means is this fourth order energy actually correctly reproduces the low symmetry structures of this phase and their relative energies. And here again, what he did is to get these Greek letter coefficients from DFT, which turn out to be these numbers, which don't necessarily mean much, right? The relative signs of these third order terms are important, but let me not get into those. What we can do, however, now is instead of performing a DFT relaxation, we can analytically minimize, well, numerically precisely minimize the Landau free energy expansion because it's a polynomial. And when you do a DFT relaxation, there's, especially in low symmetry systems, there's always the question of whether you get stuck in a local minimum and whether you find, even when you have the right symmetry, you might not have the correct structural parameters if you are not careful. But the thing with these free energies is that it's a polynomial. I can really precisely find the global minimum of any fourth order polynomial, even though it's like it's a function of 6 different parameters. And when we do that, we found the staggered triagonal phase to be the 0 temperature ground state of the structure of this compound, which seems to be in line with experimental observations, though at a really low temperature, there are other things going on with superconductivity topology and the so-called loop current phases that the whole story about these Kagome metals are a bit more complicated than I make them sound like here. But they were this paper that we cite here was a really nice application of essentially all the group theory tools that I told you about in these 2 presentations along with DFT. So the take-home message that I would like to finish with is not anything about the details of what I said, but I just want to say that group theory provides a range of very useful tools that can help both support and explain first principle studies, okay? So I think each DFT person should know some degree of group theory to really make their results more solid. And the other thing I want to say is, unlike the case, the state of the field, say 20 or 30 years ago, now there are some really good online crystallography resources, in particular this Bilbao crystallography server and the isotope software suite that are still being developed. So every year new functionalities are added to these. And these resources provide very practical implementations to perform otherwise extremely tedious, possible but tedious group theoretical calculations and predictions. With this, I would like to thank you very much for your attention and also the organizers once again for having me here. And I will be happy to take any questions if we have any time left.
Some questions to run until the students are thinking of it. Was this crystal structure proved experimentally so far, or?
Yes, there are experiments going on, and there were a few different reports. There are, and well, you have done more structured determination than I did in your life, I guess, so you would know better how sometimes different groups actually disagree about the results.
But is there still a debate about the low temperature crystal structure?
Somewhat, yes. Not, I think so. What I show here seems to be the most likely one. There is one group, however, that group seems to have better crystals, which have a slightly different structure with a longer periodicity. So that I didn't even get into. And the other issue is, it looks like there are some, I mentioned them briefly, loop current phases that break time reversal symmetry. So those are effects beyond DFT, and it looks like they have some subtle structural effects that are mostly visible in Raman, but not as much in X-ray diffraction. So yeah, the true story is a bit more complicated than I make it sound like here.
And the collaborators, they are experimentally, so you have single crystals of this material, or?
So I don't work, well, I work with some experimentals, though not the growers directly, but yeah, so there are some single crystals. Stephen Wilson in UC Santa Barbara grows them, as well as there are a few other groups. I think there's one group in China who also has single crystals. The main issue is many of these phases that I mentioned. For example, the 2 on the right, they exactly have the same supercell with the same symmetry, with identical symmetry, literally, that the positions of the Bragg peaks are identical. So what you really need is to look at the intensities of the Bragg peaks.
Yes.
And the displacements we are talking about are not huge displacements. So it turns out that it's just like
The reason I'm mentioning this, because recently one of my collaborators from UK, he does single crystal diffraction, solved a lot of crystal structures in his life. But he came up with a method where when you have systems like this, you can use diffuse scattering to sort out the crystal structure. So, for example, we had a system where you had 3 elements which had the same Z factor, the same scattering power in neutrons, so you could not sort out what's happening. But using diffuse scattering in very high Q, like L equal to 10, diffuse scattering, we saw clear signature of one transition, tiny distortion of one atom. But without that one, you cannot explain the diffuse scattering, where of course diffuse scattering comes from phonons.
Yeah.
That's why I was wondering if somebody has like decent single crystals of this, one could measure a few things together. I mean, standard diffraction, pair distribution, diffuse scattering, and then you can clearly sort out. I mean, this method is for this kind of systems where all the methods are failing. Diffuse scattering is a good way to, because you look at the phonon dispersion, the whole brilliance zone.
Yeah,
Not just some parts.
yes. There was a group with at Argonne, I believe, who looked into the diffuse scattering of this. They were. I know more about a theory paper where they were doing machine learning related to figure out to process the diffuse scattering data essentially. So I'm not sure where that went in the end. So I didn't quite follow up with the details. But as I said, these are very popular materials nowadays.
I mean, I read a few papers about actually this material over the last few months for other reasons, but I looked a bit into them. And the second question with the Landau free energy, so the reason you are doing this phenomenological theory is to make sure you get the global minima, because as you pointed out, in DFT sometimes you can get global minima, because in DFT you can get local minima. So
yeah.
So the way is to bring finer temperature effects to DFT and get global minima. That's the reason why you're doing these kind of things.
I mean the way that I would, well, the way, I don't think there isn't a very simple way to get the finite temperature effects in DFT. One thing we did in this study is, I don't have it on my slides now, but we said, okay, well, the simplest way to get the finite temperature effects is just considering these second order coefficients, alpha m and alpha l, to scale linearly with temperature. So that allows us to like sketch some like poor man's phase diagram as a function of temperature, which works okay. Like it says, okay, like
gives you the right direction qualitatively, not quantitatively, but
yeah, correct. Yeah. So in that sense, yes, we can say that yes, we got some finite temperature effects. But the main reason I think is really to find the global minimum, because like
I mean, these things are nice. I don't know too much about them. I want to learn, but they are nice tools which can guide you quite well in many directions.
Yeah.
Okay.
Thank
you. Thank you, Suran. So I'll send an email later today for the slides.
Okay, great.
Yeah, if somebody wants, other students want, probably they should send you an email to get the.
Yeah, again, anyone, if you want to send an email, send it to me. And I didn't quite advertise for our graduate program as well, but I think we have some undergrads too, right, in the audience. So if you want to apply to grad school, Minnesota is a great place. So, well, anyway, email me and we can chat. I shouldn't advertise.
Thank you. Thank you, the students.